Let's talk about waves for a minute. Waves in general are a disturbance in a medium, but waves can come in different frequencies. So how does it affect anything else? Well, the speed of a wave stays constant in a certain medium. So all waves of the same type travel at the same speed in the same medium. So we just talk about sound for a bit. Okay, I've got 3 tuning forks here. We've got a 256, which is a C, a 320, which apparently is a E, and 480 hertz, which is a B. Now, if we line these up together, 256, 320, and 480, notice that the higher the frequency, the smaller the tuning fork. So since all sound waves are traveling the same speed in the same medium, that means the velocity is fixed. So if frequency goes up, wavelength goes down. And correspondingly, the size of the tuning fork goes down. And so the longer the wave, the lower the frequency. The shorter the wave, the higher the frequency. You get that same thing if you do a xylophone or one of these pan flutes. Okay. The longer tube is going to play the lower note, and the shorter tube is going to play the higher note. And I can't play pan flutes. Have no talent whatsoever on it. But if you had a xylophone, now that will work pretty good with my musical ability. I just have to hit something. And we're going to try that with another one. This one is a giant tuning fork. This one's 256 as it's set up here. And so if I play it, we get that noise. So if I play it, we get this noise. Now, that's its natural frequency. That's the frequency something normally vibrates at. No, it's not a great definition, but it works. So these things, this is cut to have a natural frequency of 256 hertz. This one is made to have a natural frequency of 320 hertz. And our third one was cut to a length so that it has a natural frequency of 480 hertz. So this one, with the weights set up as they are, has a natural frequency of 256 hertz. Now we can do some neat things with it. I've got another one of these tuning forks that's also set up to the same frequency. And I want to set this one over for a little bit. So if I play this one and touch here, it stops. Okay, because I'm around an antinode. A node would be down here. This would be a node because there's no disturbance. There's very little amplitude there. So you can touch that part without messing up the wave. But if you touch near the antinode, you'll kill the wave. So if I touch up here, I'll kill it. If I touch here, it's fine. But here, it stops. Well, I've got another tuning fork set up to the exact same frequency. And what I'm going to try to demonstrate is what's called a sympathetic vibration, where you make something vibrate at its natural frequency by simply playing that frequency. So if I get this one going and stop it, you're hearing this one. And it doesn't matter which way I go with it. I can hit this one, stop it, and now you're hearing this one. So that's a sympathetic vibration, when you make something vibrate at the frequency it normally vibrates at. Now, you can only do it at that frequency. If I adjust these weights on this one, so now it's no longer the same frequency as this one. And try that. So I hit this one and stop it. This one's not playing at all. It only works if you're right at that same natural frequency. Now, while I've got these two set to different frequencies, I want to show you something else. Interference. And interference comes in two different types, constructive and destructive. Constructive is when two waves overlap and their amplitudes add, so the wave gets stronger at that point. So if it's sound, it's louder. If it's light, it's brighter. Destructive interference is when the two waves overlap and they're the opposite of each other. So where you have a crest on one wave, you have a trough on the other. If you have a compression on one wave, you have a rarefaction on the other. And that diminishes the wave, and so the overall result is it gets quieter if it's sound, gets dimmer if it's light. Well, something else that happens, and we're going to do this with sound, is you get something known as beats. That's when these two waves are passing through each other, and they will alternate between constructive and destructive interference. So I haven't tried this out to see how this one's set up, but it should be a lot of beats because I've really changed the frequency of this one over here. So if I play both of them at the same time, you hear that kind of rattle? I want to slow it down by making these closer to the same frequency. They're not going to be exact, but let's try this one again. Hear that high-low, 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 high-low? That's the number of beats. If you count the number of beats, that's the difference in the two frequencies here. This one's 256. So if we hear 4 beats, that means this has got to be 260 or 252. It's got to be 4 hertz off from each other if you hear 4 beats a second. A forced vibration is when you make something vibrate at a frequency it doesn't want to. This board, that's kind of what you get. But if I take a tuning fork, this one is 256, and strike it, I don't know if you can hear it very well, but that's 256 hertz. But when I touch it to the board, you should hear an increase in amplitude because I'm forcing this whole board to vibrate at 256 hertz. So when this can only move so much air, this is much bigger so it can move more air and amplify the sound. It doesn't matter which frequency I use. This one is 480. Notice how much louder it gets when I force this whole board to vibrate at 480 hertz.